Welcome to podcast 7.4. I know what you're thinking. Mr. Elegante, these podcasts, they're out of this world. Well, I know that was kind of cheesy, but I am standing on the moon. It is made of cheese. All right, well, enough about this. Let's get back to the real world. Let's see what the real world. That was good. All right. Today we're going to talk about one more type of K, KSP. KSP talks about, is something going to dissolve or not? And if it's going to dissolve, how much of it is going to dissolve? And then if you have a solution and you add a little bit more, will something precipitate out? When we write a KSP expression, same thing, products over reactants, but look at the reaction. There's only aqueous things on the right and only a solid on the left. Therefore, anytime you write a KSP expression, it's only going to be in one line. There will be no denominator. You still have to do the trick where you square some things or cube some things depending on how many ions there are. But you can do that. That's not a big deal. In a broad sense, the bigger the value of KSP, the more the solid will turn into ions, or the more soluble something is. We can define solubility as the grams of something that will dissolve, and when it dissolves, it will form a saturated solution. So the most number of grams that you can fit into a solution. We could stop one step short and figure out the molar solubility, how many moles will dissolve until it becomes saturated, or we can just write the KSP number. And the KSP says this is the ratio of ions when it's saturated. In order to solve one of these problems, you do the same things we've been doing for a while. You write the equation. What comes next? That's write an ice table. I, C, E. We start off with 0 of the 2 ions because we started with nothing but solid. The silver goes up by 2x because of the coefficient, and the sulfate only goes up by x. You know the KSP value, so we just substitute the KSP value into the equation. We solve for x, and x comes out to be 1.5 times 10 to the negative 2 moles of silver sulfate per liter. That'd be the molar solubility. You could also go all the way to grams per liter. Another type of problem might be that if they tell you the initial quantities of ions in solution, is that too much? Is it oversaturated? Is a precipitate going to happen because you've got too much stuff dissolved? That's really just a function of Q versus K again. You're saying, this is where I am now. I'll compare that to my KSP value, and I can tell you whether or not Q is greater than K or K is greater than Q. Because if K is greater than Q, that means there's too much stuff dissolved. It'll shift back to the left, and when it shifts back to the left, a precipitate will form. If Q is less than K, then that means it's not saturated yet. Still more stuff can dissolve into solution. So to solve this problem, we'd want to start out with, well, let's figure out the initial concentrations. So we take the number of grams, we change it to the number of moles, and we take the number of moles and change it to molarity. Now that I have my initial concentrations, I slap it into my expression to find Q. Remember, Q is where we are at right now. The KSP value is 1.1 times 10 to the negative 12. So remember, when you start with K, the arrow points the way. So is K greater than Q, or is K less than Q? In this case, K is greater than Q, and when you start with K, the arrow points the way. That means more solid can dissolve. It'll shift to the right, and there's not too much in there, so no precipitation will occur. Sometimes you can have problems that discuss what we call the common ion. Lead iodide dissolves into lead and iodide. Normally we would start with 0 lead and 0 iodide. The common ion is the idea of, what if we add something else that has that iodide ion? Let's add some sodium iodide. Well, we wouldn't be starting with 0 of the iodide ion. We'd actually be starting with some iodide ion. And that's going to reduce how much of the lead iodide can dissolve in solution, because we've already got some iodide there. Here's an example. Silver chloride is notoriously not very soluble. It has a very small KSP. And the KSP of silver chloride is right here, 1.6 times 10 to the negative 10th. So what happens if you start out with 0.1 molar NaCl to start with? The common ion is the chloride. So we'd build an ice table. The silver would be 0. The chloride would be 0.1. The change would be plus X and plus X. And we'd end up with this equation right here. And we'd make the assumption. So you get the silver is equal to 1.6 times 10 to the negative 10th divided by 0.1. The silver solubility in this particular solution would be 1.6 times 10 to the negative 9th. That's all the silver that would dissolve. Normally, silver chloride solution, the silver can get up to 1.3 times 10 to the negative 5th. That's when there's no chloride added initially. So if you look at the equation, AgCl turns into Ag ion and Cl ion. If you added chloride by adding a common ion, it would shift to the left, meaning there'd be less silver that can dissolve in solution. This just puts a number to it. We can actually calculate how much silver would actually dissolve into solution. This is an example of KSP in action. I have just regular sodium chloride in my shaker, and I'm going to dump a bunch of it in the water. And as you can see me adding it, you can see it dissolving. Let's see if that's enough. Add a whole bunch. Now, am I saturated? Yes, I am. Let's look over here at the numbers. At saturation, there's 181 sodium and 181 chloride ions. And let's see what happens when I add some more. No more dissolves. And if we pause and look again, still 181. So we are at a saturated point. We could actually find a KSP for this. We would take the number of molecules, 181 sodiums, divide it by Avogadro's number, and that would give us the number of moles of sodium that is dissolved. We do the same thing for chloride, and we would divide it by the volume. You'd have a concentration of sodium and a concentration of chloride. And here's the math magically done for you. If we multiply those two concentrations together, we will get a K value that is actually quite large, because sodium chloride is very soluble. But let's pick a less soluble salt. Let's pick over here silver bromide. Silver arsenate is fun because there are 3 silvers for every 1 arsenate ion, and it is very insoluble. So let's give it a shake. Are we saturated yet? Nope. The Q, where we are right now, is less than K. K is greater than Q. Therefore, it'll shift over to the right if I add some more, because we're not saturated. Let me add some more. Still not. Looks like I'm finally saturated. There on the bottom, I've got a pile that just will not dissolve. Let's pause and take a look at the numbers. There's 257 silvers dissolved and only 78 arsenates dissolved. But remember, there's a 3-to-1 ratio of silvers to arsenates. We could do the same thing. Take 257 silvers, divide it by Avogadro's number to get the number of moles. Take the number of arsenates, divide it by Avogadro's number and get the number of moles. Divide it by the volume, which is 1 times 10 to the negative 16th liters. This is a very small beaker. And we could figure out the solubility, and we could figure out the concentrations of the silver and the arsenate at its saturated point, or at equilibrium. This would be the equation for the dissolving of silver arsenate. The KSP expression is just going to be equal to the silver ion cubed times the arsenate ion. No one cares about this for an ice table. We're going to start with 0 silver, 0 arsenate. This is going to go up by some factor 3x. This is going to go up by some factor x. And we could plug into our KSP expression. But we don't really need to do that because we already know the concentrations of the silver and the arsenate from our handy dandy simulation. So we could plug in there and find a KSP for silver arsenate. And we'll actually do that in class one day. Since we have time, let's play with it a little bit. What do you think will happen if I let some of the solution out? Will the concentration get greater or go down or stay the same? So I let some liquid out. When it reestablishes whatever's going on, you'll notice the numbers of dissolved silvers and arsenates are about the same. Just because you took some of the liquid out, it's still saturated. That's not going to affect it at all. On the other side, what happens if I add some water? I added a bunch of water, but look on the bottom. It's still saturated. And if we pause and take a look at the numbers over here on the right, it's still a 273 to 87 ratio. It's just not changing that much. If I add enough water, all of a sudden it becomes unsaturated, and we're back to the point where I can shake it and see if I can get it to precipitate again. That's the magic of KSP. It's not that bad. It's just an extension of what we've been doing the whole time. We'll see you later.